Let's do that. All right. Okay. All right. Welcome, everyone, to Albuquerque, New Mexico's first meetup in machine learning. I'm Sabri Sanser, your host for today. I want to first thank Steve Kizuk and Bruce Pitts, the founders of Mountain Vector Energy, for sponsoring this event. Mountain Vector Energy is an Albuquerque-based startup which has a patent on real-time utility usage and costs, and you can check them out at mountainvector.com. I am thrilled to have Dr. Szilard Pafka as our inaugural speaker. He's a world-renowned expert in data science, and I'm honored to have known and learned from him these past couple of years. He's an author, a frequent speaker, and visiting faculty member at UCLA in Los Angeles and at the Central European University in Budapest. So we'll have a question and answer period following his talk. So please post your questions in the chat room. Also, if you could mute your mics, because I do hear some background noise sometimes. So without further ado, let's please welcome Dr. Szilard Pafka.
Thank you. Thank you so much for inviting me. It's a pleasure to talk at the very first meetup.
It's awesome.
So, and thank you for the introduction. So I don't need to do that. And quick legal disclaimer. So when people are talking about machine learning, a lot of times in the media, based on what you hear now in the media, you would think machine learning is something like this. While actually we have had machine learning for 30, 40 years in many business applications, in fraud detection, in credit scoring, in marketing analytics, in manufacturing, insurance, telecoms, and more recently, spam filtering, recommendation engines, detecting computer vision, then in virtual environments like playing games, and we hope that we are getting somewhere with self-driving cars as well. But to me, machine learning is more like this. So it's basically fitting a function to some data, and this function can be a simple linear function, or can be also not very sophisticated nearest neighbor classifier, but it can also be something more complicated, and we'll see later in this talk. And unfortunately, the media makes it quite a hype of even linear models. Everything now is artificial intelligence, and it's a little bit ridiculous what you encounter lately in blog posts and articles and so forth. And in some cases, this is even outright fraud. So a lot of times when people claim they have some kind of machine learning, it's humans labeling things in the background. And most practitioners, like myself, we don't really like to say that this is AI. I know by now the media uses interchangeably machine learning and AI, but still most people in the field like to talk about that they are working in machine learning. So in this talk, I will give you 10 tips about some best practices if you want to use machine learning in business applications. And just 10 because it's a round number. I added a few more tips in some kind of backup slides, but we'll simply not have time to talk about those. But I will share the slides, so you will see more things in those slides. So my first tip would be use the right algorithm. And a lot of people are saying lately that deep learning is the best machine learning algorithm ever. It beats anything else, so you don't really need any other algorithms. And indeed, deep learning is great in computer vision, images, image recognition. Also had some success with time series, LSTMs, and in virtual environment combined with reinforcement learning, it can really produce wonders. For example, in the game of Go, it really beat the world champions. But in business applications, we don't really have infinite amount of data that we can generate, and we can have the computers learn. So in most business applications, it's actually other algorithms who are performing at least as well, if not better, than deep learning. For example, gradient boosting is one such algorithm, probably the most successful. So for a while, XGBoost, one of the implementations, was winning 2/3 of Kaggles. The ones mainly with tabular data typically encountered in business applications, those Kaggles were won typically with gradient boosting, while the image and speech recognition, those kind of problems were won with deep learning. So here's kind of my version of Andrew Yang's slide about deep learning beating everything else, and you just need more data, and then it's always deep learning the best. So my very quick recommendation would be that if you have tabular data, so most of us are working in businesses, they want to make money, and these business problems, the data is in some relational database, and there are connections there, there are relations, and then the problem can be formulated as a prediction problem, maybe with this kind of tabular structure data. So in those cases, it's mostly GBMs, random forest, who are the best. If you have very little data, like in medical field or in some other fields, few hundred observations, that GBMs, random forest, deep learning would probably all overfit. So you have to lose some simple models like linear regression or logistic regression, decision trees or rules, or something very simple or very regularized. If you have a lot of data, again, it will become computationally too hard to use GBM, random forest, or deep learning. You probably also want to go back to logistic regression, linear regression. And if you have images, speech, and this kind of data, yeah, by all means, use deep learning. Deep learning is really the best on those problems. So a better advice would be that it depends. So my actual advice would be try them all. So there are like 4 or 5 algorithms that are usually winning most competitions, or they are the best in terms of accuracy. Try them all. Do also hyperparameter tuning of models. This way you can improve the accuracy. Another tip to improve accuracy is ensemble. So nowadays, the only way to win Kaggles is to run a lot of models and then combine them in the ensemble, because that gives you a little bit of more edge of accuracy. And that's in the real world as well. Feature engineering, I will say a few more words later. It's very important how you transform the data before you do machine learning. And sometimes accuracy is not paramount. So sometimes it's not the most important thing. There might be applications where you want to understand the model, or you are required by law to understand the model. And in those cases, you might resort to more explainable models like linear models. So if we look at what people are using actually in the field, it seems that a lot of people are using simple models. So when they have to solve real business problems, a lot of people are using simple models. You see logistic regression, decision trees, they always show up top in these surveys. So if I ask people who follow me on Twitter what they are using, those random forest GBMs, they show up a lot, just because I tweet a lot about those. So this is a little bit biased. But you see that especially in business problems, it's not really deep learning, or it's definitely not always deep learning that's the best. So second tip, use open source, R or Python. Open source is great because it's free. You can use it with no cost in a startup. But I think by now open source is better for many other reasons. For example, because of a great community, like there are meetups such as this one. There is documentation, lots of books on R, Python, machine learning, and the sort of, you can ask questions on Stack Overflow. You can often get faster and better help than with commercial software. So I switched to open source to R from MATLAB in 2006, and the cost was not a factor. It was more like the features of the language, and that I could do everything in R, and sometimes some things even better than in the commercial software. So here are some of the things I use. They all open source. This is for machine learning, R, Python, scikit-learn. VoPoWabit is for like problems with a lot of inputs like columns. H2O, XGBoost for boosting, XGBoost for neural networks, Kerals. So I think if you ask around, especially on Twitter, this might be biased, but still most people nowadays use open source for machine learning. And this was not at all like this. So in 2005, it was a completely different picture. So you can see that the commercial software dominated the surveys. So if you want to know a little bit more about which packages, I have several talks on this, especially on gradient boosting. So I'm comparing all the most commonly used gradient boosting machine libraries. They're all open source. I will post the link to the slides so you will see this. And just a quick overview of that talk. So I'm comparing here the H2 XGBoost, like GBM Cat Boost, training time and on different, and accuracy on different size data sets. And here there is also comparison of more like a feature comparison. So tip number 3, I think simple is always better than complex. So I had, before that benchmark I just mentioned, I had another benchmark in which I looked at also other algorithms like random forest, linear models, etc., neural networks. And big data was, this was 2015, big data was a big hype and everybody wanted to use Spark for everything. And for machine learning, it's not really good. It turns out that it was like 10 times slower, sometimes 100 slower than the other libraries. It was using a lot of memory. So for machine learning, forget distributed machine learning. Very rarely you use this, you need in a project distributed machine learning. It's too complex and the tools are too rudimentary, they are slow, and they are still full of bugs. So just stay away from that. And by the way, still for like gradient boosting, you can beat Spark's gradient boosting implementation on a cluster of say 10 powerful servers. You can beat it with a laptop with the right library. And most people don't really have, for most projects, don't really have huge data sets. So for machine learning, a few people have like hundreds of millions of records, but even those you can still do machine learning on those on one server. So you don't need distributed computing. Yeah, this is an old tweet, and you would save a lot of money by just not running your machine learning or acquiring a Hadoop cluster or Spark cluster for machine learning. And even Netflix open sourced this library, and they realized that even for 100 million records, it's better to design a high performance library that they can use for their problems. It was still enough. If Netflix doesn't need distributed machine learning, you probably don't need it either. And by now, people have realized that they need faster machine learning and not really machine learning that works on bigger data. Another tip would be incorporate domain knowledge. This is like do feature engineering. This is the data transformation you do before you do machine learning. And before that, you do exploration of your data, clean your data. So feature engineering is taking the raw data and creating features. For example, let's say you have web click logs per user, and then you combine the clicks from the same user and the timing and those things into feature that are specific to those users. And then you do machine learning on those users. So it's a kind of like joining, aggregating, this kind of, usually that kind of data munging that you do in feature engineering. So a lot of people in computer vision, they claim that deep learning takes care of feature engineering, it replaces it. And that is true in computer vision, but still for business problems, no algorithm, including deep learning, will figure out things like when is Thanksgiving, or why are sales high on Thanksgiving, and when is Thanksgiving. So you would have to input that manually into the features. Clean your data, very important. If your data is garbage, then garbage in, garbage out will apply to machine learning as well. Cleaning data is indeed tedious, so machine learning is actually easy. You just use some, most of the time you just use some libraries that are open source and you just download and start using them. But cleaning data is tedious. And cleaning data, we've been doing it for long. This is a book from the 90s, and this is a book from the 60s. It's actually probably John Tukey is considered the first data scientist ever. He wrote these books in the 60s, and he laid the foundation of exploratory data analysis. And then visualization is a big component of exploratory data analysis. It helps you find the outliers, error in the data, and fix them. And that's very important, that otherwise it will completely ruin your machine learning model. So this is some kind of workflow what you do in machine learning. So you have raw data, then you do feature engineering. This is the one I just talked about. And then you train the model, you evaluate it, and then you deploy it, and then you start using it for scoring and in your application. And I will use this slide a few more times. So another tip would be do proper validation. Like the very basic is avoid overfitting and data leakage. Overfitting is in every single machine learning textbook. Data leakage is a little bit more practical thing. So evaluate those models. And my favorite book for understanding machine learning is Elements of Statistical Learning. And basically, the basic idea is that if you train your machine learning model on a training sample, then you have to use a separate test sample for evaluating. Otherwise, you just fool yourself. You would think if you measure your performance on the same data that you use for training, you fool yourself. It will completely underestimate the true error. And actually, by increasing the complexity of the model, moving in this graph from the left to the right, you can actually further reduce the training error. But actually the real error, what you should measure on a separate test set will actually increase. So you are not doing any good to yourself. So here are a few examples. A linear model is something that it's on the left side of this with low model complexity, and then Here is the nearest neighbor. Here would be one nearest neighbor that it's overfitting, obviously. You see that this is the characteristic of overfitting, that it tries to fit the function to every single point of data, and it's just not gonna generalize well. And then here are some neural nets, and here is like the optimal classifier you can do with this data. So what you do in machine learning, this is the most basic, is split your data into train and test, or do what's called cross validation. That's a more sophisticated way of doing this. And then if you do several models, then you have to split it in three: train and validation for comparing the different models, and then a final test set in which you will test the final model. And you can do that with cross validation. This is something very basic. This is important, I think, this slide, because it's missing for most machine learning textbooks. If you have this kind of time series component, and you always have it in real life, then you have to do cross-validation in a time-sensitive way. So you cannot put something in a training set that it's in the future of the data points in the test set. So the test endpoint should always be in time later than the ones that you use for training. Otherwise, you would predict the past. That's kind of very easy to do, and you're just fooling yourself again. So that's kind of a cheating, and it's also one form of data leakage, which a lot of people are doing in Kaggle competitions, but also it's easy to do it in real life. So don't use any information from the future. I added this to my original talk, model debugging. This is about understanding the models. And this happens very often. So, and we don't really know how often, and we don't really know about it. So, for example, there is this great paper about Rich Caruana. You can Google it and read it. So they were doing machine learning on trying to predict the risk of death by pneumonia. And their machine learning model learned something weird, that people who had asthma had lower risk of dying from pneumonia, which was really weird. But this was something, a real pattern in the data. So the machine learning model, if they use this machine learning model, it would have been totally garbage, and it would have been dangerous. It would say that people with asthma are fine, they are low risk. So the reason for this is that actually people, because doctor knows that people with asthma are higher risk, so they send them directly to the ICU, and they receive much more aggressive treatment, and that's why their risk of dying was lower. So models trained on this data would be actually harmful. So and a lot of times we in other applications we don't really know. So we have to investigate. This is the whole idea of model debugging. Do we have this kind of patterns in the data that would make the machine learning model do completely bad things? So some of the methods, so again, this is not really in textbooks. I really recommend Patrick Hall's GitHub repositories. This is one of them. He talks about some of the methods that are older and some of the newer ones. So one of the older ones are partial dependence plot and ICE. This allow you to see the, basically we're trying to understand this function, the function that we are fitting with machine learning. And let's say if you expect that the function monotonic, then you would see this kind of monotonic behavior in the partial dependence plot and ICE. If you don't see that, then something is wrong. Another method, which is very new but much more powerful, is Shapley values. If you do machine learning and you never heard of Shapley values, then look up, read about them. They are also very useful investigative tool. And you can also, Shapley value is basically decomposing the function into components that depend only on one variable. And this allows you, again, in a better way that, so ICE and partial dependence plots, they have various different disadvantages, and with Shapley values, you can do something better. You can better diagnose problems. And then you can also use them for variable importance. So understanding which variables are more important. This is more like a global understanding of the model. So another tip, batch or real-time scoring. So once you have your model, you deploy it in production, you're gonna score. This can happen in batches, let's say every hour or every 5 minutes, or it can happen real time. It's much easier to implement batch prediction because you just get some data from the database that needs to be scored, and then you score it. It's the fancy folks are advocating for like for real-time scoring, which can be, if you want to do it the fancy way, then it's gonna be like a web service, like a REST API and whatnot. But actually, if you ask people in the field, still more of them are using batch scoring because that's good enough for their problems. So for example, if you want to select for marketing purposes who you're gonna send email, you don't you can have a cron job that runs every hour or every day and then makes that selection. You don't have to have real-time scoring. And technically, real-time scoring is more complicated. But there are tools that can do it well. So one of them, open source, is H2O. So I have a GitHub repo where I looked at what open source libraries can score very fast because I needed that. So if you need that, then by all means do real-time scoring. You can take a look at this GitHub repo. Unfortunately, if you do with R Python, then it's much slower than this. So if you really need like very fast scoring, then look at this. Besides validation, like avoid overfitting and those kind of things, you also need to do online validation. Also, a lot of people are not doing this. So you need to evaluate the models also based on the scores that you get in real life. Because, and you can find very little. This is kind of probably the only article that talks on the internet about this, or there are very few. This is probably the best. It's from a company that used to be called GraphLab, and then Dato and Turi, and then they disappeared, unfortunately. But the problem is still very important. So you want to evaluate your model online because there is a lot of bugs that can happen in your implementation in the online scoring pipeline, because you need to replicate all the feature engineering you did during the training. So by comparing this, by doing this online evaluation and comparing it with the offline evaluation data, you could see if there are discrepancies. And tip number 8, monitor your models. Also, unfortunately, not everyone is monitoring their models. You want to know if the model starts spitting really bad scores. So you want to have some kind of graphical representation of scores and also some kind of alerts. This is a blog post. Again, not many people are talking about that, especially not in textbooks. There is this blog post from Retention Science. That's a startup in Santa Monica. Maybe some of you here in the audience worked for Retention Science or worked for them. So they wrote a blog post about their machine learning monitoring tools, which is basically graphs and alerts. And alerts should go in email, Slack, or text, or something that would alert you to look at these graphs if something happened. So basically you can look at distribution of the scores. You can alert if there are too many, let's say, high score items within last, I don't know, 5 minutes, 1 hour, depending on your use case. I asked again how many are using machine learning monitoring tools. This 50% sounds a bit too optimistic. So I don't think, and based on what I ask at meetups, how many people are using monitoring, I think it's less. It's probably some kind of sample selection bias that people who don't use, they just didn't answer the survey. Another tip, when you evaluate, look at business value. So machine learning textbooks are about evaluating machine learning models based on like ROC curve and AUC and this kind of metrics. But your boss, the only metric your boss cares is money, is dollars. So you need to evaluate the machine learning model based on the impact it makes in that business use case. And again, there are very few blog posts or articles about this or papers. It's completely missing from machine learning textbooks. There is one here by the guys at MLDB. So basically you try to evaluate the cost of, let's say, false positives and the benefits of true positives and all that. And this is how you can define a utility, and then you, instead of maximizing AUC or something like that, or choosing the threshold to be on a certain part of the ROC curve, you can try to choose the threshold to maximize this kind of utilities, which would be the money impact in your business application. And of course, estimating the impact exactly, it would be very difficult. So you don't really need that, but at least do something like back of the envelope kind of calculation of what would be the impact of your machine learning model. So number 10, make it reproducible. This is very important. There is for everyone heard, there is a reproducibility crisis in science. A lot of papers cannot be, the results cannot be replicated. It's because people didn't leave a good trace of what they were doing when they were doing this research. So for machine learning projects, I think that having a reproducible way of doing things it helps you with debugging things, and it's also like it enhances trust, and it's also a kind of like a productivity benefit. So basically what I'm talking about is use tools like IPython Notebook or in RStudio Markdown, and put your code in such a way that you can generate those results with pushing a single button. So both in Python and R, you have these wonderful tools in which you can integrate your whole analysis, and then you push a button and you redo it. This is a productivity issue because maybe 3 months down the line, your boss asks you to redo that analysis on the new data, and then all you have to do is just push that button, and you don't need to do a lot of manual work. So the anti-pattern for that would be something like this that I've seen a long time ago, but I'm sure it's still there in a lot of organizations. So running some SQL query, copy pasting the results into Excel, creating manually this kind of Excel graphs, and then copy pasting them in PowerPoint, and then giving all this kind of crazy names for the latest version. So I guess that's pretty much it for the 10 tips. And I guess we can, I can stop here. I can show you the slides. I have a lot more extra tips, something like 30, 40 more slides. We might talk about some of that if those show up at the question. So 10 is because I wanted to fit it in this like 35, 40 minutes, which I kind of did amazingly, even though we went through kind of like more than 100 slides. So I guess, Sabri, now we can open for questions.
Yeah, no, thank you so much. Wow, just I learned a lot myself, especially with tip number 10. Didn't realize the reproducibility was an issue. Yeah, please feel free to send your questions in chat. There was an earlier question by Stephen. Would be
Oh yeah, sorry, I didn't see the chat. Yeah. Let me open the chat.
See methods used versus methods sold. Could you clarify that, Stephen? Maybe in chat, or if you want to talk, if he's still there. Oh, some folks want the extra tips as well. So.
All right. So first of all, before people are leaving, if they are busy, I'm gonna post the link to the slides. Let me post that.
Yeah.
And then we can go from there.
I do have a couple questions. Like for someone that's new in the data science world, how would you? Do you have any recommendations on how to get started, like for a student or?
Yeah, yeah, I started data science and machine learning like more than 10 years ago, and it was kind of a pain because there were only a few books, a few blog posts, this kind of things on freely available on the internet. But now it's I think the bottleneck is your time. So there are almost like too many of them. Like Coursera has great courses. Then there is I mean, if you are very ambitious, then the elements of statistical learning, the book I was referencing in the slides, that has a free downloadable PDF version. But otherwise, for a lighter introduction is probably Coursera. And the rest, there are tons of blog posts also. So I posted the slides.
Oh, in the chat? Okay.
Yeah.
Another question is a company that wants to get into data vision or data science or machine learning. What avenues? Because they may not find the resources, person-wise. Are there consulting companies or how would you recommend a company get started? I guess.
Starting with what exactly kind of problems?
No, let's say a company, an engineering company has no idea of how to get into machine learning, but they want to get involved. They have a lot of data. Who can they talk to, or who do they turn to?
Yeah, I think they can do what my company did like 15 years ago. They hired a data scientist, or even before it was called data science. So I think either they hire data scientists. There is now a lot of data scientists available. The other thing they can do, they can grow internally. So you can grow someone from engineering or maybe some from business. So basically data science is kind of a combination of analysis and then machine learning model development. So part of it is more like an analyst kind of thing. The other part is more like engineering. So there are people from engineering, and there is also people from business that they go into data science. And then there is also all this kind of people in very quantitative fields like physics, like myself, chemistry, bioinformatics, and those kind of folks who have the quantitative background, and they go into machine learning data science. And of course, the classic is the CS. A lot of in a lot of CS basically courses there is a machine learning specialization.
Awesome. Did you see the chat? Yeah, more questions are coming in.
Okay, let me see the chat. If I recall correctly, back in LA, you mentioned that there is a faulty installation of XGBoost and the correct installation. I don't remember about that. I think, or maybe for, I think maybe, yeah, maybe for Python, but only if you use the, only if you use Anaconda. I think there is XGBoost and Pi-XGBoost, I think, if I remember well, but I don't really. But I think the one that was faulty didn't even install, so you would know, you would notice. Yeah, can you tell me your top 3 classification algorithms that can handle imbalanced data sets well? I think if I have imbalanced data set, I would rather first balance it and then use the algorithms that I would use anyway. And there are many ways to balance data sets. So one is to downsample the majority class. This would, you would think that it loses a lot of data because you're throwing away a lot of data, but actually it might work pretty well. You can also augment the minority class to make more data and to balance it that way. And there are several Bayesian, more sophisticated ways of doing that. But in all those things, you basically, there is also always a trade-off. So many times the sophisticated Bayesian algorithms, they introduce some kind of information that it's not there in the data, and then they make things worse. So I would start first by just downsampling the majority class into something that, if it's not 1-to-1, but let's say the majority class is 10-to-1, then downsample it to, I don't know, 1-to-1 and also to 2-to-1 or 1.5-to-1 and see what happens. And then most algorithms would work with that kind of balanced data. Yeah, do you mind sharing your thoughts on LightGBM, XGBoost, CatBoost on data sets with categorical features with high cardinality? Yeah, again, kind of depends. So I would say again here is like be opportunistic. So try them all and see which one performs better. But also within each of them, you have different ways of dealing with categoricals. So CatBoost has a lot of blog posts that they tell you that CatBoost is the best for categorical data, which is completely untrue. So try all of them. So most people in Kaggle, where they want to get the best results, they try all of them. And also there are different ways of dealing with categorical. So you can, with XGBoost, I think the only way is to do one-hot encoding. With LightGBM, you can do this kind of, it encodes it to numerical values. So, and that's faster. You can always encode to numerical values, but then you would lose some of the structure of the data. And then there is also like target encoding. I think if you just Google your question, kind of, then you would already find some good results of a few blog posts that are discussing the advantages and disadvantages. But a lot of times it's not sure it's gonna work for your data. So I think, yeah, probably the best is take the time and do different kind of encodings and use different implementations, and of course do the hyperparameter tuning for all those models. Right. Do you have any favorite tools on techniques for time series data? I used Facebook Prophet in the past. No, I'm not working too much with time series as per se. So they are time data, but they are not really time series. So yeah, but from what I heard, Facebook Prophet is uh, probably pretty good. There is also like Hindman has. If you're using R, then look at Hindman's blog post. So he's kind of like the biggest name in time series data.
Szilard, there's earlier questions too.
Yeah, I'm not, yeah. I
Actually,
realized
okay.
that I was looking from the. Let's now go from the top. Yeah, it would be interesting to see methods used versus methods sold. Yeah, if you look at my talk on GBMs, which is like a 40-minute talk, then I'm comparing Light GBM, XGBoost, um, H2O, and CatBoost. And those, I also did a survey of what GBM libraries people are using. And also, let's not dismiss random forest. That's also a very good method. And neural networks, of course, for if your problem is like that. Yeah, could you share the slides? Yeah, I shared. Maybe let's make that even more prominently.
Yeah, Szilard, can you show the previous slide? I think you had a link to your Twitter and all your other links.
Oh, yeah.
Or 11, I'm sorry, 11. Yeah, 11 tips. Yeah, this one. Perfect.
Let's do.
And another question was, any tips on data versioning?
On versioning of the data, no, not really. So there is. I mean, there is a few commercial applications that are trying to solve that problem, and also one open source. I don't really remember the name, but I'm not super familiar.
And then what books would you recommend? How would you recommend that someone would practice machine learning? I guess that would be in your link, probably. Okay.
Yeah. So I think if you are very ambitious, then I would recommend the Hasty Tipshirani book, The Elements of Statistical Learning. This one. And this has the free PDF download. But for this, you have to have, I would say, a few hundred hours. Yeah, otherwise, probably the faster way to get not so deep knowledge would be Coursera. So there is still, like Andrew, I said very bad things about Andrew Yang about deep learning, but actually I like him. He before doing deep learning and jumping on the hype and creating a lot of that hype, he was a professor at Stanford and he was teaching machine learning. And then he founded Coursera, and one of the first courses there was a machine learning course, and that's really great.
That was Andrew Ng, not Andrew Yang.
Yeah.
Two different people. The one other question that was here, let's see, data versioning. Any model recommendations for variable length signal processing?
Mm-hmm. Yeah, I don't know about that. I would have to pass. But I see another one here. In what scenarios do you find random forest performing better than gradient boosting? Or is it more than random and simpler and easier? No, actually, yeah, let's go to, where was the, oh, that was at the beginning. Yeah, I usually talk about gradient boosting lately, but I really like random forest as well. So a while ago, when people had data sets smaller, like let's say tens of thousands of records, then actually random forest perform better. So I think when often you would find that on like smaller data, let's say 10,000 records, random forest would beat actually GBM. And the other advantage of random forest is that you don't need to do a lot of tuning. So with GBMs, you would have to spend a lot of time tuning the model to get a good performance or to get the best performance. If you are in a hurry or if your data set is not huge, then yeah, actually random forest might be better. So with random forest, you might get faster good results and good enough results, and then you don't need to do all the tuning with GBMs. I think you can see that in Kaggle. So when Kaggle started, I think around 2010, a lot of their data sets were like of that size, less than 100,000 records. And then most of the first Kaggles were won by random forest. And then the data sets became bigger, and then GBM XGBoost took over. So yeah, I think on smaller data sets, actually random forest might beat GBM, even if you tune GBMs, no matter how much time you spend tuning them. Could you type in the chat the name of blog to refer time series? Okay. Let's see.
I guess we'll go to extra tips after this.
Yeah, so for time series, just Google for this guy, Rob Hinman. Cool. Sabri, you had a question?
Yeah, no, I'm saying let's go to extra tips then. I think.
Oh yeah, I see there are still
Oh, you
almost
see
nobody
more?
left. So I guess
Okay.
okay.
I mean,
All
for
right,
this
more.
recording.
Let me grab a sip of water and then we'll go to
Sure,
the
sure.
extra tips.
I wish I had some AI music to play.
Yeah, it's not gonna take that long. All right, so extra tips. And you guys stop me when you want to stop me.
How many tips more do you have?
I think I have another like 30 slides, but if I go this fast, probably it's gonna be like 10 minutes.
That's fine. That's fine.
Yeah, I can do it in 10 minutes probably. I never tried this because I added some of that just like the last few days. So use the cloud, by which I mean raw virtual servers. So when you train machine learning, you need a lot of CPU cores, or you might need GPUs. You need a lot of RAM, and you need it for limited time. You might train your machine learning model in a few minutes or in an hour, and then you might not need that server for a month. So the cloud is really perfect. The elasticity of the cloud is really perfect for that. So and by roles virtual servers, I mean just EC2. So you spin up the server, you install everything you need, or you have like a Docker container, and then it's all automated. It installs by itself at a push of a button, and then you use your open source machine learning tools that you would use anyway on your laptop, but now you have a lot more RAM, a lot more CPU, and then you pay only for the time you use it. And then for scoring, you can use it on separate servers. Scoring doesn't require a lot of RAM or a lot of CPUs, and if you and it scales linearly, right? So tip number 12: don't use machine learning, so-called machine learning cloud services, like machine learning as a service. So, and this is I'm talking about, let's say, Amazon's machine learning as a service, or Google Cloud, or Microsoft has something the same. And it's not only me, it's like, I think this guy puts it the best. So Brad for a Cross, in this blog post, you can read the whole blog post. It's really great. The people that know what they are doing just use open source. And the people that don't will not get anything to work ever, even with APIs. So I'm talking about these APIs where, let's say, you can train some machine learning model that you don't even know, but Google or Amazon or Microsoft said that they have the best AutoML, whatever machine learning thing, and then they will charge you a lot of money for scoring every single item. So these are typically, like, you don't know what's inside. You can probably do better. Probably inside is just open source tools that you would otherwise use anyway. But you also lose a lot of control, and then they charge you a lot of money. So just try to avoid that. Number 13, use high-level APIs in your code and not GUIs. So in machine learning, we like high-level code. You don't, here is, for example, from my benchmark, the code in Spark for train a machine learning model. And if you do that in XGBoost, in R or Python, is like 1 or 2 lines of code. So who the hell wants to write all this, like, I don't know, 30 lines of code and maintain them when you can use another tool that you can write just like 1 line of code? Much easier to write, much easier to maintain, much less error prone. So yeah, just don't use this garbage. And the other thing is also, don't go in on the other side where you use some kind of GUI tool that it's gonna generate the code, or is gonna you just need to click, because those are usually too restricted. So with the open source coding tools, you can do much better in the way, like, you can do, they are much more flexible than like a GUI tool, and they are much more efficient than something like this, like a low level API code. All right, 14. I guess we're going to the most controversial ones. I put them here. Ignore Kaggle mostly. So I think if you do Kaggle, you miss probably 80% of things that someone would do in machine learning in production. So I had this tweet, and this is kind of like a zoom of that. So in Kaggle, you never learn to clean your data enough, because they already give you some pre-clean data. Most likely there will be some data leakage, because most of the organizers of competitions, they don't know what they're doing. Then in Kaggle, the only thing that matters is accuracy, and you will fight to increase the accuracy in the 4th digit, which is completely irrelevant in practice. Then you would evaluate based on some kind of textbooks, machine learning metric like AUC, and not like a business metrics like the money impact. And the models you do for Kaggle would be probably too complex to deploy them in production. Most of the winning models from Kaggle, they are never implemented by the organizers. See also like the Netflix prize. The Netflix paid $1 million in prize, and they never used that model. In Kaggle, there is no actual deployment, there is no online evaluation, there is no monitoring, there is all this is you don't learn any of these if you just do Kaggle. So when I said ignore mostly, I mean you can learn a lot of things in Kaggles, but that's not enough. So yeah, if you want to do Kaggles, but also learn the other things. GPUs, again, it kind of depends. I didn't expect GPUs to be that great. For example, this is not machine learning. I had a benchmark also on like data munging, aggregation, and joining in databases and other tools like R and Python, like let's say in pandas. And then this is like aggregation time and join time, and notice the logarithmic scale. So some of the tools on the like up right corner, then they can be like 100 times slower than the tools in the lower left corner. And it happens that this one is running on GPUs. So MapD, when I did the slide, it was actually it was kind of a new. Now there are many other GPU-based SQL engines, and the same for machine learning. So gradient boosting GBMs got several implementations on GPUs. So some of them are still buggy and not very stable, but I would say that XGBoost is now kind of the fastest, the most memory efficient, and also the most stable implementation. So if you have a GPU, then now you can run XGBoost. It's a different code base than the CPU-based XGBoost, and it's as fast as like GBM on CPU, and on like larger data, it can be actually faster. But then again, so GPU, you would have to fit in the memory of the GPU. You have to fit the data. Okay, tuning AutoML, again, something that it depends. There is this blog post that compares various very sophisticated tuning methods to just random search. Random search is when it's like a grid search in which you pick points at random. It's much more efficient than the random search. There is another article that's really good comparison of grid search and random search. I should insert this for next time. So random search is better than grid search, but it's also very simple to implement, and it's almost as good as all the sophisticated Bayesian optimization methods. And then there is also another paper that is benchmarking the various AutoML frameworks like Teapot and H2O's AutoML and AutoScikit-learn. Here's the link to the paper, and they do it on different problems. And then what's kind of disappointing is, if you are a big fan of the hype, is that basically no AutoML system consistently outperformed the others. And on some data sets, they were only a little bit better than random forest. And on some data sets, they were actually worse than an untuned random forest, which is kind of a disaster. So you have all this you have all this hype in the media that like the machine learning will train itself and will learn itself and AutoML. And meanwhile, they are not even beating a random forest on many kind of practical data sets. And then I have another GitHub repo in which I looked at if you train a lot of models, or if there are a lot of competitors in a Kaggle, and the test set is not big enough, then the winner is gonna be random at some extent. So basically, the smaller the data test set size and the more the models, the more this randomness will appear. So let's say if you have 10,000 observations for evaluating a Kaggle competition, for example, and you have 1,000 participants, then it's very likely that actually the winner is not really gonna be the best model. It just happens to be the best on that test set. And actually, if you go with 3,000 competitors, then the whole competition will be completely bullshit. So it's gonna be a random winner, actually. Okay, so ignore the hype. That's kind of like the meta advice. So don't go for the fanciest technology just because there are a lot of hype about it and a lot of blog posts. It's probably not gonna work for your problem. So these are some of the contenders for the biggest bullshit. Is this AI? I couldn't resist asking this question on Twitter. Like, what are you doing? Is it machine learning or AI or neither of them? So you see the 3% AI, and then a few minutes later, the guy posted that, oh, sorry, I meant neither. I fat thumb pressed AI. But actually, so the survey continued, and then there were a brave 7% of people who said that they are doing AI. How to start with machine learning? I would say that try to do a kind of proof of concept thing in your organization and try to prove that that project would provide some monetary value. There is nothing better than money that talks to your boss. And actually doing this is not super difficult. So the tools are open source. You download them, you train your models, and then you can score it on some test data and show your boss that you can predict something and that can be useful for the business. So I guess I'm not sure how long it took, but this is pretty much the end. And then I put again the my contacts.
Thanks, Szilard. No, this is awesome. You do have one question in the chat.
Yeah, let me see the chat.
Sure.
Do you think that things may change soon with regard to cloud ML platforms, Google Cloud, and clicking tools? Do you think they may get much better in the next 2-3 years? I mean, it's kind of hard to predict, but I think so there were several attempts in Amazon and Google to do some kind of internal tool, and they didn't want to use open source tools, and then they did something that was much worse in performance because they kind of like to design something for like big data or some other use case that most people don't have, and then it has terrible performance on most of the use cases that people do have. So yeah, I'm not really very optimistic. So I would say that if you are decently senior in machine learning, you can learn how to use the open source tools, and you can probably do as well as anyone else with commercial tools. And you have seen that all the open source, so that benchmark of open source platforms was of AutoML platforms was about open source AutoML. We don't really know what Google is doing. So Google has a big marketing on the neural network side, but that's more like for computer vision and those kind of problems. And now they have something for tabular data, and they also say that that's pretty good. we don't know. We have to see. So I mean, nothing stops people to use those services and win Kaggle. So I think Kaggle. I said a lot of bad things about Kaggle, but one thing is really good is kind of like a test bed of algorithm performance. So if something is good, then people are gonna use it for Kaggles, and then we will see that. So for now, it's basically gradient boosting, say XGBoost or LightGBM, for tabular data and deep learning for like images and those kind of like speech and those kind of data. Um, but we'll see. So if you just follow Kaggle, what will pop up if something is really that good that it beats everything else, then it will pop up in Kaggle. Oh, if your boss mandated and cloud ML service tabular data, what would you choose? Yeah, I'm not. Yeah, yeah. My boss will not mandate me doing that. So I have a great boss. So, uh, uh, and actually, two at the top of the company. So they are super smart, and they would never mandate using such thing. But yeah, I didn't really follow what happened with. Then the other thing is that also like a lot of people like transparency, like open source is pretty transparent, and machine learning is kind of already very complicated, but at least you have some degree of transparency with open source. But with the cloud services, you don't really know what they're doing. So like the Google Cloud Tabular thing, we don't really know what's happening. The other ones, they don't really have GBMs. So some of them, they have, some of the cloud services are like, I think the Microsoft one is you can use LightGBM, but then why wouldn't you use just LightGBM yourself as open source? And I think Amazon doesn't really have, or in the one of the parts of the services, and in the other part, it kind of also has open source. So the cloud services now are like partially they are like on top of open source, so they can do exactly the same as open source. So you can do it yourself. And the other one is like we don't know, and they don't have some of the algorithms, or the ones who have, which Google Cloud Tabular, we'll have to see how good is that. But that's more like an AutoML kind of thing. So we probably have to compare it to AutoML tools.
Cool. Awesome. I think we'll end here. Dr. Pafka. No, thank you so much again. And thanks to everyone that came to our first Albuquerque machine learning meetup. And I couldn't have asked for a better inaugural speaker. Really, and a great presentation. I'll post the link to this recording on our meetup site, and also Szilard, you're going to post this to Data Science, right? .la, I think.
Yeah, absolutely.
Places. Cool.
So
awesome.
Thank you. Yeah, thank you so much for inviting me. It was a great experience. Thank you.
This is great. No connection issues. I know you're in Budapest, so it's awesome. Cool. Thank you.
All right. Thanks.
All right. Bye, everyone.
Bye-bye.